Okay, so let's continue. From yesterday, we said that we're going to study together this semester the electromagnetic waves, and the waves, as you have seen them partially in the last couple of weeks of the previous semester, we have already seen those because we could derive from equations, from Maxwell's equations, we could derive the wave equation forms, and the Maxwell's equation, this is what they were for the divergence. So you had the, if we write them this way, this would be either B or magnetic field intensity, and the divergences and the curls, they provided for us relations that were such as this form, dB over dt, and then we have the other divergence, which is rho over epsilon 0, the curl of H of B. So we always have this the curl of the fluxes. It is always the time derivative of the intensities of the respective fields, and this is something which is always equal to 0. This is always equal to 0 because the magnetic monopoles, they have not been found yet. Okay, so we have not been able to observe the magnetic monopoles. That's why the divergence of B is always equal to 0. So this is always where we start from. In the phasor notation, we could modify this a little bit, meaning that this could be equal to minus J omega V, and here we might have something like mu 0 J plus J omega D, because in the phasor notation we often try to represent a wave such as, for example, E can be equal to E0 e to the power J omega T e to the power minus J kz, for example. Okay, so we have a wave here where we have the time propagator, so we can call it this way, and we have also the space propagator, which describes to us how this is going to vary as a function of space. Now, these two, and of course we can combine these two for sure. We know what the units of these quantities here are, but whenever we calculate the time derivative, the dE over dt, this will often be something like, whenever we take this derivative here, we get this j omega term, j omega times E0 times e to the power j omega t times the spatial or spatial. Myself, when I was a student, I was confused when I say spatial because it was speciale, but it is spatial, spatial. So in principle, this is simply equal to j omega times the E itself. Okay, so for this reason, often in the phasor notation, so whenever we use this phasor notation, this is how the Maxwell's equation can be reformulated or restated. Okay, so this is and then what we could do is that we could combine, for example, these two wave equations, and then if we combine two first-order differential equations, we can get only one, but this will be a second order differential equation, which makes things a little more difficult. Okay, so and then actually the level of difficulty, it will be almost the same, but this part you can just simply try to remember it this way. Whenever we solve the first order differential equation, we have one constant. Okay, because we have to figure out one boundary value condition to find one constant for a first order differential equation. If we have a second order differential equation, we need to have two boundary conditions because we will have two constants. In the principle is something like this. So we can have, for example, dy over dt is equal to 4y. This is a first order differential equation. And whenever we integrate, this is trouble, which means that it's a trouble because once we integrate, we should be able to be very good experimentalists to figure out what is the constant of integral. This is a huge problem in science. Okay, that's why taking derivatives or solving differential equations is very difficult, which means that integrating is challenging or more troublesome. But taking the derivatives is always easy. If we have, so this is the difficulty of integrating. And the easy part of taking the differential. So taking the derivative of y is equal to 3x squared plus 5x plus any constant k. This is easy because these constants, they are gone once we take the derivative. Okay, but once we integrate, that's a problem. For example, even in the 100 years ago, when electromagnetism was being formulated better and better experiments were formulated, there was a time when even Einstein, who was very sad that in the university there was no course on electromagnetism or electromagnetic waves. This was just the time when they figured out that the light has a speed which was equal to 3 times 10 to the power 8. This was a huge revolution. But what I want to argue for you, which might be, it will be very intuitive, and you can use this line of thinking for many other similar problems. The problem is that the biggest problem 100 years ago was that when the electrons were accelerated in a particle accelerator, in order to calculate the energy, they used to integrate, right? So they used to integrate the force applied by an accelerator, but it never made it there because the electron, it was not accelerating anymore. Okay, we know now the reason, because the speed of light is the upper limit, and electrons cannot push further than that. So if they just use the integral, they were not able to calculate what was going to be the last state of the electron. Okay, so in principle, taking integral is very difficult because you have to come up with a new constant c. Okay, so in this case, the integral, you know how to take these integrals over y. This is equal to 4 dt. You integrate both sides of the equation. This is ln y. So far, everything is good. 4t plus c. This is the constant of integral. This is one constant of integral if you have the first order differential equation. If you have second order differential equation, things will end up being like this. Second order derivative of dy over dt squared. This would be equal, let's say, 4y. And then the first integral, so you have to integrate here by multiplying both sides by dt. So you are going to obtain, so let's assume first that we don't have this one here. The first derivative dy over dt, this is going to be equal to 4t plus the constant c1. Then you integrate it again. Then you have, this is 4t squared over 2 plus c1t plus c2. Now, I believe you already knew this one so far, but in principle, what I might say is that whenever we work with differential equations, often we end up combining two first-order differential equations like these to get a single one, but which is second-order differential equation. What did we gain? We gain a better understanding probably of the same wave, but we have two constants to figure out. And these equations, most of the time, they will always end up like this. The second space derivative of electromagnetic field, this is equal to 1 over c squared dE over dt squared. So these were the waves. And then the relevant parameters regarding the waves that we are working with, they were the k, the beta, or the phase constant that we have seen them at least yesterday. So, for example, this simple equation, this can also be written in such a form. So we can formulate this one also. This is a k squared times e, because there is a relationship between the speed of light, which appears here, and this k. But let's see an example. And for this example, let's take out this conceptual discussion on the ability to better calculate the integral or better calculate the derivatives. And let's okay, so here we are given a single wave of the, or let's say this is the electric field representative of a wave which is composed of two associating electric and magnetic field. Now, which is the E and the H, because in here we always have these that are coupled. As long as we see a time dependence here, most probably we are going to have also a magnetic field associated with this one, because it changes the function of time, right? Because a rate of change in E produces a magnetic field. So now, what should we do here to find the H? To find the H, all we need to do is that we have just to pick up any one of these four equations and insert the E and get the
H with the curl of E.
Sorry?
The H is founded by the curl of E. But it's not.
That's true. Yes, we can try that one. And the curl of E, in this case, we can formulate this one like this. The curl of E, this is equal to minus j omega B. Okay, that's it. So we know E. So we know this this element. We have to figure out this one. So it looks like a pretty simple or almost straightforward result. You're right. This is how we can go with it. And then we need to find the curl. And by the way, once we try to find the curl, we should also try to see how much information is written on the board. First important information that is written on the board, it is the amplitude of the electric field, which is 0.02 volt per meter, okay, which is 20 millivolts per meter. The amplitude apparently is 0. That's one important parameter. Another important parameter is, out of this constant that we have here, which one is given? What can you see? The parameter of time, where does it appear? P. 7.5, that's true. So this is the, but what is this section here? This is omega, right? So if this is omega, then we can also, but this is the angular frequency. So that means that we also know the frequency itself. So apparently this omega, which is equal to 2 phi times the frequency, this is equal to 7.5 times 10 to the power 8. And of course, the unit here, it will be radian per second. So if we divide by 2 pi this value, we can find the frequency. So apparently the frequency we are operating with, it's going to be something like this frequency. 7.5 divided by 2 pi. Let's give it like this, times 10 to the power 8. So this is like approximately 0.1 gigahertz, or 100 megahertz, in the order of 100 megahertz frequency-wise. So around, is it 100? Yes. So apparently we also know this much. What else can we extract from here? So if we know the frequency, we can also find what is the wavelength. The wavelength.
Speed of light.
That's true. So speed of light, we can also check the units. The units can remind us of the correct expression. So this is going to be 3 times 10 to the power 8 divided by the frequency, which in this case is going to be, this is the frequency divided by 7.5 times 2 pi. And then here we have 10 to the power 8, right? Am I right? Yes. So in this case, 10 to the power 8, which comes from the speed of light, divided by the 10 to the power 8, we have here 6 pi. Yes. Yes. So apparently we have a wavelength in the order of, so this is approximately 3 divided by 3. What is this? Around 2 meters, right? You can do the exact calculation of this one. But it looks like we have a wave. 2.4 maybe, 2.4 meters. Huh? 2.5. Okay. Approximately 2.5 meters. So apparently we have a wave, which 2.5 meters is from where I'm standing to the wall. So you can imagine a mathematical construct again, which completes a full period or over 2.5 meters. Which means that this is the mathematical construct. We have a wave which is 0. It increases. But when we talk 0, we're talking about this axis where the amplitude it is 20 millivolt. Okay, 20 millivolt per meter. And then this is in this domain. This is 2.5 meters, okay? If we use in a different domain, which is the phase, this 2.5 meters, this will correspond to 2 pi of phase difference, okay? So how much will the phase change from point A here to point B in phase, faza dămășoară 2pi, kur shkoj prapë kur përsëritet përsëri. Kurse në hapësirë ka lëvizje 2 pikë 5 metra. In time, so how much time is from this point to this point if we are progressing? So this is radian, right? In rad, this is radian, 2 pi, it's right here. Now the question is, if this is time, what is this time equal to? Huh? So, let's meter frequency, that's true, but what is the frequency? So the frequency is, because time we're looking for seconds, and the seconds are equal to 1 over hertz, which means that this is equal to 1 over the frequency, which means that 1 over the frequency, it will be equal to 1 over 7.5 times 2 pi, but then we have here let's do it like this. So what we get here, we multiply by 10, divide by 10 to the power 9, because 9, we may define this one in terms of nanoseconds. And here we get 20 pi divided by 7.5 nanoseconds. 20 pi divided by 7.5 nanoseconds. So how many nanoseconds do we have here? 20 times 3, it's around 600, divided by 7. Who knows what it is? 7 times 8, around 80, right? You can correct me on this one. So around 80 nanoseconds. So this is how much this this full wave will correspond to. Okay, so this length scales actually, for these time scales, you should always extract them right away. So once you see this piece of information, you just go ahead and find all of these, okay? So we're talking about something which changes in the order of tens of nanoseconds. You have something which is changing in the order of 2.5 meters, etc. And for example, you're working here with oscilloscopes which are very fast, and some of them, the most important parameter that you might look in these oscilloscopes is the frequency. Can you read the frequency? Just you have a look, scan it a little bit on the parameters that you can observe. This is a function generator, okay, but I believe this is a spectrum analyzer. Somebody over there is not here, or here. You can see this one, this oscilloscope. Can you see what frequency this device is?
9 kilohertz.
9 kilohertz, but it should be in the fuzz.
No,
try to read parameters on this one. Or
then you can get gigahertz.
But there is also something which is like 1 gigahertz sample per second, which means that these devices, actually, the element that makes this expensive, what increases the price of this device, is the frequency at which it can sample a signal. It can be a signal which can be very slow. If the signal is changing very slowly in time, you may need to. So if it is 1 hertz, that means that 1 hertz in 1 second, you have a sinusoidal wave. These cosine waves that you have seen in calculus. How many data points do you need to draw a perfect cosine wave in 1 hertz? 20 data points is more than enough. 10 also it would be okay, right? So if you take 10, if you have a signal of 1 hertz, you may need to sample a signal at 10 hertz, which means that you read 10 different values per second. Okay. Now, so let's say that this is our wave that we want to measure. It takes 1 second from time 0 to 1 second. And then you need 1 data point here to read out the 0, 1 here, the second, the third, the fourth, and the fifth. Okay, so we need these because if you miss this it might not be good. Then you start to read again 5, 6, 7, 8, 9. You pick another data point here, 10. That's good. So that means that to pick up a signal at 1 hertz, you need to read at 10 hertz the sampling rate. How often you're going to measure. And then you might observe that some of these oscilloscopes, some might be less than 1 gigasample per second, which means that they're going to be cheaper. And right there, this is 1 gigasample per second, so it's going to read this much. Now, I remember there are some which are around 600 megahertz or 400 megahertz. So a good engineer, the first thing that you go and look for, this is 2 gigasamples per second, so the price can be like at least maybe 1.5 times more expensive than this one, which is sitting here. And operating at these high devices, sometimes a problem can be posed to you, which I faced this one some time ago. So I had a friend that we needed to delay a signal 5 nanoseconds. He said, I have a pulse, but I need to send it 5 nanoseconds later. So how can you send a pulse 5 nanoseconds later? You have to make a time delay. So this is signal 1, and you have another signal. Another signal 2, you have a second pulse, you are reading a data, and the question is that you want to bring this signal closer by 5 nanoseconds. So the time scale that you want to, delta t, that you want to improve or correct, it is 5 times 10 to the power minus 9. How can you do it? I mean, what choice would you provide? I used to ask this question in physics 1, okay, to students. I mean, if you have pulses, how can you make them faster? Any opinion? Any idea? Towards all waves. So how is it possible for you to have 2 signals which come from a BNC cable that looks like this? So this is the first input. We call it channel 1, channel 2. You can have an input signal from any external signals which you can put here. But how can you make a signal 5 nanoseconds earlier or later? Any idea? So now this is your time scale. The time scale is of this order. So always, what you should be very good at, or should be also an element of your intuition, is you should always relate length scales with time scales. So the first thing I can ask you is that if your time scale is 5 nanoseconds, what is your length scale? What should you be thinking right away? how can you convert seconds into meters? How do you do that? Spezi, that's true. So you have seconds, and then you multiply with velocity, which should be meter per second, right? That's true. So this is how you can convert the seconds into meters, because these units will cancel out. But then, what is the speed you might be talking about? Speed of light, that's true. So in this case, if you have the speed of light, which is 3 times 10 to the power 8, you multiply this one with the length scale, the time scale, you should get the length scale. So you multiply this one 5 times 10 to the power minus 9, and you do the multiplications. You get here 3 times 5, this is 15, and the other terms, 10 to the power minus 9, you get 10 to the power minus 1. That's good. And then 1.5, right? So you get 1.5 meters. So we found the answer. All you need is that you have to pick up another cable which is 1.5 meter long. So you pick up this BNC cable. You just extend this one with a longer. Okay, so this is around 1.5 meters. So this length of the cable, you just extend your current cable, or you cut it shorter if you want to have the signal faster. This will convert your signal at a shorter, let's say, it will shift it left or right, earlier or later in time, by this time scale. So you should also, in the whole, whatever we're going to do in electromagnetic waves, we should always convert frequencies very fast in time, the times very fast in length scales, okay? Because this will be always your intuitive tool how to solve sometimes very wonderful problems, or let's say nice problems. So with this one, this also means that you can be very good at adjusting delays in certain signals. You can be very good, because what you can do is that what is your shortest precise piece of wire that you can make in the lab. Let's say you can make a wire which is 1 centimeter long, even 1 millimeter could be good, but you might have problems at connection. So this is another problem. But if you make 1 centimeter, that means that you can select, or you can be as good as delaying signals in the order of I don't know what. So 1 centimeter, it is 10 to the power minus 2. You multiply this one with 3 times 10 to the power 8. So what do we get here? What is this? This is length scale. So this is meters. If this is meters, we have to divide by this one, right? Because we have to divide with meters per second. Okay, that's true. So the length scale that we can adjust with this one, this would be 1/3 times 10 to the power minus 10. Okay, so this means that 1/3 times 10 to the power minus 10. This is approximately 1/3. It is 0.33 times. Let's multiply this one by 10 to the power 2 and 10 to the power minus 12. So this makes here 33. If you combine these two, picoseconds. Okay. So apparently, with very small, you don't need very high technology. You can be proud enough. You can say, okay, I can delay a signal for 33 picoseconds. Okay, that's good. If you cut this in half, you can make 15 picoseconds and so on. Okay, so that's good. So we should. So how did we get all this piece of information? How did we get educated a little more just by looking at the board? We just were careful into reading all the information, which was this specific value of omega. Then, so now we did a good job so far. Just so I can see this one. So the curl of E, in this case, let's continue with our example. We have to calculate the curl of E, and then we will have to divide by this amount to find the B. Okay, that will be the only thing we have to do. How do we do this? AX, AY, AZ. This is the derivative with respect to X, derivative with respect to Y, and derivative, partial derivative with respect to X. So this is equivalent to this, and this is equivalent to this. We're going to use this one to save time and space a lot. So let's see here. Then in the curl of E, the component of E along the x-axis, this is 0. And the component along the AY, it is 0.02 times cosine. 0.02 times cosine, yes, some terms here, and the z0 again. So when we calculate this curl, first of all, the first intuition is this. What should be the direction of the B? Magnetic field. What is going to be the direction of the magnetic field?
AY?
Huh?
Why?
AY. Well, AY is already taken by Leon Nelson, but no, it's about the electric field. So AY, we know that magnetic field and the electric field, they are orthogonal, which means that if the electric field is along the AY, the magnetic field is along the AX and AZ. Okay, that's the only possible direction. But in this case, since the wave, it looks like it's propagating along the z-axis, most probably the magnetic field might be along the AY, right? Because we have a triplet in three-dimensional space. We have three orthogonal directions. Okay, we don't have a fourth one, which means that the propagation of the wave, which is often denoted by a vector k. Here we have the E, and here we have the B. Okay, so in this case, most probably the B might end up being along the x direction, okay, because the z direction is taken by the k vector. But the point is that the k is not always pointing along an orthogonal direction. The k might be pointing along x and y. That means that the other b will also be along the x and y. But we're going to see these examples in the future weeks, which in principle, these are really often you might not see this like a very difficult task. It's rather a very wonderful exercise for you to understand space. Whatever you used to do in linear algebra with space and how things develop in three-dimensional space. So just assume this is a very wonderful exercise which adds more to your intuition. So now, okay, so we go ahead with this, and the curl of the magnetic field, this will simply be, well, let's try, we said that the first candidate is AX. Let's see what we get. We get here the derivative of 0 with respect to y, which is 0, minus the derivative of this term with respect to z. What is the derivative of this term with respect to z? This is 0 minus the amplitude is here. Then we have cosine omega t minus beta z. Okay. Then AY, here you have minus AY, which means that the derivative of this 0 with respect to x, which will be 0, minus the derivative of this other component, which is 0 with respect to z. So you have no doubt that this will be simply, I'm just taking a little bit of your time, but it might be always, it was almost obvious that this would be 0 plus AZ, which in this case, we have the derivative of this term with respect to x minus the derivative, so we have to look at this one, right? Minus the derivative of the 0 with respect to y. But in this case, what is the derivative of this expression with respect to x? So, okay, there is no x, so we get just 0 minus 0, whatever. So we are left with only this term. So the derivative of this cosine with respect to z, first of all, it is going to be minus sine, because the derivative of cosine is minus sine. This is equal to ax. We have minus here, minus. Let's keep this minus. Then we have let's try the amplitude. This is 0.02. Then we take the derivative of cosine, which is minus sine. So let's add this minus sine. And sine also has the arguments of omega t minus beta z. And then we have to take the derivative also of this term inside, right? We have another minus beta, is it correct? Times minus beta. So in the end, we get something like this is equal to ax times minus sine is sine minus beta. So this becomes minus 0.02 beta minus 0.02 beta times sine omega t minus beta z. Okay, so this is the curl of E. So we can write this one right here. So this is going to be equal. So this was our essential equation. So this becomes AX or minus AX 0.02 beta times sine. These arguments will all be the same. Okay, so inside of this sign, we are going to see always this group of terms. Okay, this is how the phase of the wave is going to change. It is going to change both as a function of time. Later in time, of course, it's going to change a little bit, and then later in space, as it propagates in space, it's also going to change a little bit. And what is interesting is that imagine for a moment you might awaken your intuition little bit by little bit. So you assume now that you are sitting with this photon, which is coming a signal from somewhere, and you are moving in space. So for that, or you are sitting on top of an electromagnetic wave, and you're propagating in space, which means that you are going to change, but you're also moving in time. So those two components, we can discuss again about this one later. Those two components will be inside that function. So apparently, we found what is the B, because all we need to do is that, let's take this out. So here we have so then we can cancel out these minus signs, then B will be equal to AX so we found the B. If we need to find also the H, we know that the H is equal to B divided by mu. Okay, so we found also the H. Now, what happens here is that within all of these equations, there is an important aspect that this beta. So another question is that can we find beta? I cannot beta. Huh?
K.
Say it again.
It's the same as K.
That's true. Yes, it is related strongly to K, or it is the same as K, because this is e to the power kz or beta z. And this K, this is the vector, the propagation vector, which is very strongly related also with the speed of light. Okay, so it is not an independent variable. That beta, it is sitting out there like that. But we should be able, or we could be able also to calculate that one. Now, that is because this K or beta is something like this actually. Okay, so, and now you know the lambda, we found it because lambda was related to omega through frequency and through speed of light. So we can get all of these. But another trick that we can use is also that now that we know H, we can use another Maxwell's equation, which relates the curl of H so out of the Maxwell's equations, we can apply another curl to find this, and this would also be equal to J omega times permittivity times E. Okay, so if we calculate another curl, and then we can find the curl of this one, of this term here. We substitute everything here, and maybe we can do it. It should not take us too much time. So this is AX. Let's say AX, AY, AZ. AX, this is sine. So this curl, of H, of course, we might be expecting to get an answer along the AY for similar reasons, because if the magnetic field is along the AX, the propagation is along the AZ, then we might expect an AY right away, which is going to look like this. AY will be equal to the derivative of 0 with respect to x, which is 0, minus the derivative of this term with respect to z, minus 0.02. Well, let's write it like this: p over dz of the hx. Okay, because this is, in principle, this is really just hx. We get here y minus 1, and then we continue. We have the derivative with respect to z. What is the derivative with respect to z of this term? The derivative of sine, it is equal to plus sine, sorry, cosine. We get here cosine with a lot of other terms, times the minus beta. This is minus beta. And then we have the amplitude terms, which would be 0.02 beta. So I believe this is all, okay? And these, in fact, these two are equal to each other. So the curl of H is equal to these whole terms in here. So then, let's try to simplify this one a little bit. So we have here AY. This is minus beta. This becomes plus beta. This plus beta with another beta here becomes beta squared. So this is 0.02 beta squared over j omega mu cosine. So I think this is all we have on this side. This would be equal to the square root of minus 1 omega permittivity times the electric field. Now the electric field, we can substitute what we had at the beginning, okay? So we can substitute because we knew that one. It should be equal to that one that we had initially, right? We took the curl twice because we used the Maxwell's equation twice. How did we do it? We found the curl of H, of E, and the curl of H. And in the end, let's substitute this one. This is AY times 0.02. And then we have the cosine term. So we look at these expressions. We can cancel out the cosine term. Well, we can simplify this AY, and it's just pointing for the direction. And finally, we get something like 0.02 beta squared. This is equal to
J omega squared.
Yeah, this j squared. We also have j omega squared Okay, this will be yes. Now we have to figure out what is beta, and beta in this case is 0.02, right? Oh, 0.02 also cancel out. Okay, so we can simplify this a little more. And this beta, apparently, even though we might have expected that this was an independent variable, apparently this is strongly linked with these, because what we did, we applied Maxwell's equations twice. We find out now that beta is equal to all of these terms. If we take the square root of both sides, it looks like the beta, or which is equivalent to k. Since we're going to see this quite a lot, let's take out some information here. This was just about frequencies and so let me write here k for a moment. This is going to be equal to beta. This will be equal to omega. So this is what we get from this expression that we worked out for some time during this hour. And then let's continue here. This let's write it back to beta because we might get confused. The beta is equal to omega, and omega it is 7.5 times 10 to the power 8 times the square root of this. What is this? Now we might remember that the 1 over the permeability times permittivity, this is equal to what?
The speed of light.
Speed of light squared. So this is speed of light squared. This is equal to. So you might correct me on this one. So apparently. Would you agree with this one? So you take this upside down. That means that this beta, this is simply divided by the 3 times 10 to the power 8. So we get. So we found the beta, which is 2.5. Now, what is the unit of beta? Ska? Okay. Tot așa se întâmplă cu sinusul de la? Oh, so this is equal to so this beta, it ends up to being something like, if you didn't do any mistake on the way, beta is equal to 2.5 meter inverse. Okay, so the unit of this one, it is the inverse of the of space parameter. Is there any question? Andy, Egi?